Hello everyone, my name is Qingxi.
My name is Yu Xiao.
Today we will present our final project, Imbalanced Satellite Image Classification using Positive Unlabeled Generative Adversarial Network. As an introduction, the weather prediction relies heavily on the satellite images. However, it is expensive to collect images directly from the satellites when the ground is covered by clouds. Therefore, the satellite images are usually imbalanced. We will have much more satellite samples without cloud than samples with clouds. This imbalanced data makes classification extremely hard. Therefore, in our work, we try to use generative model to create more cloudy samples to solve this problem. Specifically, we explore two different GAN models, the normal GAN and the positive unlabeled GAN. Next, I will talk about the methods we use to generate more cloudy images. The figure shows the overall framework of our model. It has two parts. The classification part is a convolutional neural network with two convolution layers and one fully connected layer. It is trained with cross-entropy loss. The generative part is either GAN or PU-GAN. The generative model uses the real cloudy data to generate more fake cloudy data. The classifier is trained on both the real data and the fake data. In our work, we compare two different GANs. The first one is just a normal GAN, and it has a min-max loss shown here. For GAN, the generator tries to generate samples to fool the discriminator, and the discriminator tries to distinguish the real data from the fake ones. GAN is a very powerful model. However, its training is in general not very stable. Another issue we observe from GAN is that the discriminator is unable to distinguish between high-quality generated samples and the low-quality generated samples. Especially in our case, the low-quality samples will make it extremely challenging for the classification task. Therefore, we also try the PU-GAN to allow the discriminator to treat the high-quality generated samples as real data. The main modification is that the discriminator tries to distinguish between high-quality image and low-quality image instead of real and fake ones. And we have a modified loss shown here. In the figure below, we compare the training loss between GAN and PU-GAN. We can observe that GAN has a very unstable loss, and it goes up and down during the training. In contrast, the PU-GAN has a much more stable generator loss and discriminator loss. Also, it is important to notice that PU-GAN converges faster than GAN. Next, my partner will share some more experimental results.
For the classification task, we trained our model with 3 different sets of training data to compare the result, and tested with 1,000 real clear and 1,000 real cloudy images. For baseline, we trained on 1,000 real clear images and 100 real cloudy images. For GAN, we trained with an additional 900 GAN-generated cloudy images to create a balanced dataset. For PU-GAN, we trained with an additional 900 PU-GAN-generated cloudy images. In all 3 methods, we trained our model with the same learning rate, batch size, and epochs. The baseline yields a 73% test accuracy, GAN yields a 88% test accuracy, and PU-GAN yields a 97% test accuracy. The test result indicates that the generated high-quality cloudy images improve the classifier performance. We also did a controlled experiment training with 1,000 real clear and 1,000 real cloudy images and got 98% test accuracy. The accuracy trained with PU-GAN is very close to the controlled experiment, so the generated images by PU-GAN work nearly as good as real data for classification. The confusion matrix shows that the true positive rate remains very high for all 3 methods. However, the true negative rate of PU-GAN outperforms both the baseline and GAN, which indicates that the generated cloudy images by PU-GAN help the model to generalize much better. It is also interesting to notice that the false negative rate of PU-GAN is slightly higher than the baseline and GAN, which means that the generated cloudy images from PU GAN could minorly hurt the performance of the model. To summarize, we conclude that the training of PU GAN is more stable than GAN. With our method, we achieve a 31% increase in classification accuracy when training with PU GAN generated data. For future work, we plan to explore other GAN models like BiGAN and CycleGAN to generate higher quality samples. We can also use some standard sample quality metrics in addition to human perception to evaluate local patterns of pixel intendencies and smoothness. Thank you very much.